Parallel processing is the core idea of modern computing. Computers have evolved from single-core machines to multi-threaded machines to today's tensor processing engines, which process thousands of channels in parallel. As I hope you understand from this course, the modern camera is basically a computer with sensing resources embedded in the computational architecture. A lens, of course, processes the field in parallel, but as we've just seen, the radiance in the focal plane of a lens does not fully characterize the optical data cube. So here we see a picture of an array of lenses that is drawn by Dolly. But the idea behind this is that perhaps we could capture the field better if we do parallel processing, like processing in multiple lenses, even though the lens itself is parallel. The core issue is, what should the granularity be? How should you design lens arrays and lens hierarchical systems to process the field and fully capture the field most effectively? Here's one approach to that. This is the Litro planoptic camera, which uses micro lenses in front of the focal plane to get some diversity in the sampling. This particular approach is not adaptive and gives up a lot of transverse resolution, really for no reason, because you can capture the same information with intelligent adaptive sampling. Here's another approach using a heterogeneous array camera. This oversamples the field in the sense that the wide field camera captures the same information that narrow field cameras capture, but here the system can be adapted to adjust sampling rate, processing complexity, and resolution across the field. This is a hard problem, figuring out exactly how you should design sampling systems to fully get the information that you want and process it and deliver it in real time. We'll talk about this throughout the rest of the course. Today we're going to start that conversation by looking at the possibility that lenses could be designed to emphasize different parts of the spectrum, the spatial spectrum of the field, and then we would use arrays of such lenses to capture the field. Let's get to it. Computational Imaging. Episode 53, Point Spread Function Diversity. Here we're looking at a design for a folded optical system. This has an annular aperture because the clear aperture is here at the edge, and then the light path comes through and bounces around, coming to a focal surface here. This system has somewhere 20-25 millimeter focal length, but the overall thickness is well under 10 millimeters. So obviously you get an advantage by having a thinner optical system with a long focal length, but you pay a cost in the MTF, as you see here, that this is the diffraction limited MTF, and then this is the MTF as realized in this system for various field points. This is a very narrow field of view system. If you come in at oblique angles, the optical performance will suffer severely. The midband frequencies are suppressed. Always the peak is at DC, of course, and then here at the high frequencies, the MTF is slightly above the diffraction limited MTF. Let's talk about how that works. Back when we first introduced MTF, we considered an annular aperture, and we found that first of all, this was the PSF that we get, which has a lot more side lobes than the PSF that you get for a well-formed diffraction limited PSF. But you have this little increase in the MTF at high frequency. Now, the MTF is a plot of the relative transfer of different spatial frequencies. So overall, the total energy in the system is reduced by the annular block, but the relative passband is increased at the high frequencies compared to what you'd get with the diffraction limited system. So today we want to talk about whether this is a good idea, whether you actually get better SNR at the high frequencies than you would get if you didn't block the center frequencies. Okay, so this uses a Jupyter Notebook, which is on our course GitHub site. You can go look at high-pass filtering of incoherent images. The first example in the notebook considers the transfer function for a one-dimensional aperture. So here's our transfer function, or MTF in the case of the incoherent system. The actual aperture, the pupil function, goes from minus 0.5 to 0.5. But we're only looking at the positive valued spatial frequencies here. And so if we take this square wave and convolve it with itself, we get the triangle function, which is our incoherent transfer function of the optical transfer function. Now, if we have a annular one-dimensional aperture, we've blocked the center frequencies, and so we have this square wave which ends at 0.5 but begins at some frequency less than 0.5, and then would also have a negative frequency corresponding part. If we take this shifted square wave and convolve it with itself, we have the square wave here and the square wave in the negative frequencies convolving with themselves at the DC. So we get a peak as always for the zero frequency, but this square at the high frequencies convolve with itself, and you get a peak that's half as high as the peak at the DC. So here at this spatial frequency out close to 1, we're getting half of the overall MTF relative to DC. And we've designed this system so that the maximum coherent spatial frequency is still 0.5 over lambda f, and so the maximum incoherent frequency is still 1 over lambda f. Okay, so that's so in here, for comparison, we have the diffraction limited MTF in green, and so this is our comparison of the MTF that we would get with clear aperture and with this high pass filter. So let's look at what this transfer function does to a harmonic function. So let's suppose that our incoherent image is I naught plus some I1 times cosine of U1 x. So U1 is the spatial frequency of the signal that we want to measure. If we measure that signal through this transfer function, then as you would expect, the high frequency component is attenuated by this factor. So we get an image of the system, but with lower contrast, because we get unitary passband for the DC, and the high frequency is attenuated as shown here. Okay, now if we compare what we get for the high pass system, this factor out in front, the bandpass is the width of the annulus here. This B is the width of the annulus, and the energy we get through is attenuated as we make B smaller and smaller. But we get the signal we get would be the DC signal, and then the high frequency is attenuated by 1/2. So obviously, if this factor that we got from the incoherent system is greater than 1/2, so if we're over here where this is greater than 1/2, then the high pass signal is worse than the conventional clear aperture signal. But if we're out here where U is more than 0.75, it turns out that we can get a stronger signal than we would get with the clear aperture. Okay, we can look at the Fisher information. If we want to estimate I1, here we're assuming that the only unknown parameter we want to estimate is this I1. We find the Fisher information under Poisson noise by taking the derivative of the measured signal with respect to the unknown, squaring it, and then dividing it by the measurement. You can go back to Chapter 2 and review Fisher information to understand that formula. And we integrate that over all the measurement positions, and that gives us the total Fisher information for I1. And so this is that value for the clear aperture. This is the corresponding result for the high pass aperture. Now we've accounted for the reduction in energy due to the annulus, and we see that we get this result. We can assume here that I1 is much less than I naught, just to simplify our formulas. And if we do that, we get the Fisher information for the clear aperture depends on the length of the window that we're going to integrate over to estimate the signal. It depends inversely on the energy in the DC term, and then it's reduced by this MTF factor. In comparison, this is the Fisher information under the same limit where I1 is much less than I naught for the high pass system. And now there's no longer frequency dependent in the Fisher information because we're assuming that we're measuring the frequency at the peak of the high pass signal where the transfer function is 1/2 of the DC transfer function. So this is the ratio of those two Fisher informations. And what you see is that if this U1, the frequency we want to measure, here we've chosen B to optimize the Fisher information for I1. So we've chosen B to be peaked at U1 and it has to go to 0 at the transfer function has to go to 0 at u equals 1 over lambda f number. So now if we choose, if u1 is, so that we have this factor of 4 here, and so this factor is going to get small as u1 increases. So if u1 was small, the coherent impulse, the clear aperture Fisher information is 4 times the Fisher information for the high pass signal. But if u1 is bigger than 0.75, then this factor will be less than 1/4, and this ratio will start to increase. And as u1 gets close to 1 over lambda f number, the Fisher information can be substantially increased relative to the clear aperture. So it turns out that if you wanted to measure this high frequency, this could be a useful strategy. Now, you couldn't just make your aperture bigger, of course, and then you'd have a better signal at the high frequencies. But we're assuming here that you have some limit in the size of the aperture, and you're going to think about maybe you should use a lens array where you're going to measure different parts of the spatial spectrum or different parts of the system with different apertures. The Jupyter Notebook includes a simulation of doing that for a 2-dimensional aperture. Here we assume that we have 2 lens systems with impulse responses H1 and H2. The first one has a clear aperture, and the second one has an annulus that allows us to emphasize the high frequencies. Now we have to say, well, how are we going to combine the data from these 2 camera systems? As we'll talk about later in the course, probably the best way to do that would be to develop a neural operator to do the combination. But if we just want to look at what this could mean for the signal-to-noise ratio, it's simple to think about using a Wiener filter. We imagine we develop a joint Wiener filter that would take the image from the first aperture and the image from the second aperture and combine them linearly with some jointly optimized Wiener filter here in the frequency space, and then take the Fourier transform to get our recovered image. We can solve for what the minimum mean square error Wiener filter looks like under this assumption. We've assumed here that the images are, that the cameras are aligned and that there's no calibration problems, and so we just assume we can apply this Wiener filter and add the images together, and we've solved for the minimum mean square error operator under the assumption that we know the signal-to-noise ratio for each of the cameras, and we know the transfer functions. If we do that and analyze what the impact is on the signal-to-noise ratio, of course, if we had only the annulus, then the error would be bad over here where the spatial frequency is less than 0.75. But because we're combining these 2 apertures, our relative error never goes below the error that we would have for the clear aperture alone. So here we're comparing the mean square error. So this black curve is the clear aperture alone. The blue curve is when we've added the information from the annulus. And you see that near the edge of the band, we get up to 4 times improvement in the transfer function. Now, this is the important thing to understand when we look at the optical transfer function. The reason the optical transfer function is interesting is it's a map, really, of the mean square error that you'd get at different frequencies under the assumption that the error is, that we have Poisson noise and the error is coming from all the frequencies combined. So in this situation where we suppress, we increase parts of the transfer function relative to others, we can improve the relative mean square error, even if this is the case with an annulus that we've blocked part of the light. Now you could just say, well, I want to make a bigger lens instead of trying to combine this or use this kind of annular filter. But in fact, it is a useful strategy from not just this issue of how to optimize the error, but how to package the lenses and how to sample and process to do parallel processing. So that's the point here, is that this is a big design space, and these ideas of designing with multiple apertures and figuring out how to combine them is a theme that we'll come back to over and over again. What we've been through in the last few episodes is extensions to the conventional theory of cameras. We first derived the conventional optical transfer function and talked about the defocus transfer function. But now we've seen that it would be useful for us to measure coherence in the focal plane. It's useful for us to have some diversity. So these are challenging the model of what we're measuring in the focal plane, that we should be more interested in exactly what the data that we measure at the output of the impulse of the forward model of an imaging system is. We haven't talked much about the input to the forward model. We've just assumed that we have this incoherent irradiance, but that assumption is also often not quite valid. Here's a movie of my hometown, Tucson, Arizona. You see these cars driving on the highway, and notice that these lights are flashing, so the glints off of the cars flash as they move around. In our simple model of imaging systems with an incoherent radiation from the remote object, the image doesn't change if we move the camera. That's different, of course, from what we saw with coherent systems, where we used motion of the camera to recover the wavefront as the phase changes. But with an incoherent system, we're not sensitive to the phase of the radiator, but what you're seeing here is that real systems are not necessarily incoherent. That the glints off of the cars is possible because they're illuminated by highly directional sunlight, and they reflect that light in a highly directional manner. So you look at down here, there's some kind of spinning object or something that is causing those glints to appear. And so we can analyze that, right? This is part of the forward model of a system. So these speculative reflections increase the complexity of the object. The object is no longer a three-dimensional object. It's a three-dimensional spatial object that also has a directional reflection. So it becomes if we include space, time, and direction of reflection and spectra, these become 7 or 8-dimensional tomography challenges to reconstruct the object. So in our next episode, we'll talk about how to represent the radiance of the object and how one might think of that as a tomographic imaging problem.